Hello again. This is Math 2233 coming to you from the College of DuPage. And this is the conclusion of the lecture entitled Vector Functions and Space Curves. And as always, be an active learner while watching this video. When we last adjourned, you were in the midst of doing this problem. I hope you did it, but we're going to work through it. I ask you to sketch this curve. Now, so r of t was equal to this. The parametric equations for this curve then are x is equal to cosine of t, y is equal to sine of t, and z is equal to t. Now, since x squared plus y squared is the same thing as cosine squared t plus sine squared t is equal to 1 for all values of t, the curve does lie on the circular cylinder. X squared plus y squared equals 1. That means the curve lies on it. It doesn't mean the curve is equal to that cylinder. It just lies on it. The point x, y, and z lies directly above the point x, y, 0, which moves counterclockwise around the circle. X squared plus y squared equals 1 in the x, y plane. And the projection of this curve onto that plane does have this equation. And so you see that you're down there in the z equals 0 plane. Now, since z is equal to t, the curve spirals upward from that. So it goes up like this around the cylinder as t increases. This curve is called a helix. The corkscrew shape of the helix is familiar from its occurrence in coiled springs. It also occurs in the model of DNA, which was discovered, at least the shape was discovered in 1953 when Watson and Crick showed that the structure of the DNA molecule is that of two linked parallel helixes that are intertwined as shown in this picture. Now, in the previous examples, we were given vector equations of curve and asked for a geometric description of them. In the next two examples, we were given geometric descriptions of a curve and asked to find parametric equations for the curve. So this example asks you, find a vector equation and parametric equation for the line segment that joins these 2 points in three-dimensional space. You know what to do. Let's see how you did. Okay, well, this is the initial point, this is the final point, so we know from prior art that this is parametric equation is r of t is equal to, this is actually the vector equation, r of t is equal to 1 minus t r0 plus t r1, and so this is what we get for the vector equation. When t is equal to 0, we're at this point. When t is equal to 1, we're at this point. And the rest is points that are in between. And the parametric equation is going to be given for this, just the components of that. And the way we arrived at this is we did simplification of this expression to get that. So those are the corresponding parametric equations. And here is a picture of that line. Notice that it starts at this one because that's what we get when t is equal to 0 and goes to this one when t is equal to 1. The next example, find a vector function that represents the curve that is the intersection of this cylinder, x squared plus y squared equals 1, and the plane, y plus z is equal to 2. You know what to do. Let's see how you did. Well, this is geometrically what's happening. There's the plane, y plus z equal 2. Here's the cylinder, x squared plus y squared equals 1. So the projection of c onto the xy plane is this circle, x squared plus y squared equals 1, z equals 0. And so we know that one way to write that parametric equation is x is equal to cosine t, y is equal to sine t, and t goes from 0 to 2 pi. Now, for the equation of the plane, then, we can have that this is y plus z. So we can say z is equal to 2 minus y. but then we substitute y being sine of t, and we get this is what z is. So the parametric equations are this is x and y, but z is this for all values of t. So the corresponding vector equation is given by this expression. Now that's what we're talking about, is parameterizing the curve C, and again you can see that it does have an orientation. Now, computers are often used to draw curve spaces, and here's a free community college program that does that, and you may want to do this to experiment some with this free, and it is online. Space curves, though, are inherently more difficult to draw than plane curves, and accurate representations often uses technology. And so, for example, this figure over here shows a computer-generated graph of one that has parametric equations that are pretty complicated here. And this is called a toroidal spiral because it lies on a torus. A torus is like a donut. Another interesting curve is called the Trifoil Knot. Here's the equations of that, and that's what the picture looks like. Now, it's difficult to tell what's really going on in this three-dimensional plot, and so there are different views that you can get with many programs. And so what we can do is we can experiment with that, drawing the curve that is given by t, t squared, and t cubed, and that's pointy bracket t, t squared, t cubed. This is called a twisted cubic, and you can see that if we look at these different views in different boxes, we can really see what's happening much more clearly than if we just look at the raw axes. We can even look at what's happening in the single plane views, and that can give a lot of insight into what is really happening with the equations. So when space curves are viewed from different angles, they appear to be different types of plane curves. These are like traces, I suppose. A designer of playground equipment often includes swing sets. The path of a child on a swing can be modeled with a space curve. When viewed from front or back, the path appears to be just a line segment. You go from here to there, back and forth, like that. But when viewed from the front or back, the path was a line segment, but when viewed from the side, it's the arc of a circle. Electrical engineers must be aware of electromagnetic fields, such as those generated by a coiled wire. The path of a particle through an electromagnetic field forms a space curve. Depending on the field, the curve can appear circular, sinusoidal, nearly elliptical, or nearly linear. And even in sports, when a pitcher throws a baseball, the path of the baseball can be modeled by a space curve. Viewed from the side, the path may appear to be parabolic, but when viewed above, the path may look almost linear. So those are examples where you would use those kinds of capabilities. Another method of visualizing a space curve is to draw it on a surface, and that's actually one of the things we did when we looked at this at the helix. For instance, the twisted cubic that we talked about lies on the parabolic cylinder, y equals x squared, and you can see that here, and you can trace it on there, and that gives you a sense of what is happening. You eliminate the parameter from the first two parametric equations, x equal t and y equal t squared. That figure shows what happens there. And so you can see the curve moves upward from the origin along the path of the cylinder. We can also use this method to revisualize the helix, and we've really already seen that. The helix plastered onto the circular cylinder. A third way for visualizing a twisted cubic or general curves is to realize that it also lies on a cylinder. This is a different cylinder, z equal x cubed. And so we can look at what happens there, and it can be viewed as the curve of intersection of the cylinders, y equal x squared and z equal x cubed. Now z equal x cubed is the one that is twisting, and it's that one, and so the curve that you're seeing is this one, the point, the intersection between those. Many space curves can be visualized as being contained within surfaces. Such curves can also be seen as intersections between surfaces. So engineers often work with springs when building machines. The shape of a spring is modeled by that of the space curve of a helix. And a helix is contained by the surface of a circular cylinder as well as a sinusoidal cylinder. When a quarterback throws a football, the path of the ball can be modeled with a space curve. Such a curve is contained in a parabolic cylinder as well as in a plane. Scientists often use electron microscopes. Such microscopes rely on the motion of particles through electromagnetic fields. The path of these particles, again, can be modeled with space curves that may be contained in hyperboloids. Now we have seen the interesting curve occurs in the model of DNA. That's the helix. Other important space curves in science are the trajectory of a positively charged particle in orthogonally oriented electrical and magnetic fields, E and B. Now, depending on the initial velocity, it can behave differently. You can get this red curve, which is projected down here, and you can recognize that this projection is in fact a well-known curve, which was the cycloid. And here, what happens is, if you have a slightly less velocity, what will happen is that the projection will be a different curve, and in this case, this is called a trochoid. Now, some computer algebra systems do provide us with a clearer picture by enclosing it within a tube, and in fact, Maple is an example of such a program. And you can look at this in a tube, which is kind of a good way to get perspective. And here's a couple of physics websites that do a lot more with the animations involved with the trajectories of physical particles. In closing now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. Until we speak again, God bless you all.